Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And salam sejahtera to everyone. This chapter we're talking about the molecular geometry. Lewis structure we learned already in the previous lecture. The Lewis structure is showing the number in the types of bonds between atoms in a molecule. It does not indicate the geometry of the molecule. For example, for this compound CCl4, from the chemical formula, I believe all of you can draw the Lewis structure. From the Lewis structure, we can know the electron domains. The electron domains is 4. It consists of 4 bonding pair of electrons, 1, 2, 3, 4, with 0 lone pair. However, from the Lewis structure, we cannot tell or we cannot indicate what is the molecular geometry. Basically, for this particular compound, the molecular geometry is like this. We call it tetrahedral. The geometry and the size of the molecules are determined by the bond angles and also the bond length. So there are 5 basic geometries of molecules. First, we have linear with angle of 180 degrees C. Second, we have trigonal planar with the angle of 120 degrees C. Third, we have tetrahedral with the angle of 109.5 degree. Fourth, we have trigonal bipyramidal with the angle of 90 degree and 120 degree. Last but not least, we have octahedral with the angle of 90 degree and 90 degree. No need to worry about the angles. You no need to remember exactly the value of the bond angles. The important things that you have to remember is the name of the molecular geometry: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and also octahedral. It is not enough only remember the name, but you must able to draw the geometry of each type of geometry. For example, linear. This is linear. Trigonal planar. You should be able to draw how to draw the trigonal planar. Trigonal and then planar. How to draw the tetrahedral, like this, 109.5 degrees C, like that. It's like the chicken feet. And how to draw the trigonal bipyramidal, straight line, and then we have in the middle, this look like a trigonal planar, like this. This is 90 degree, and this one 120 degree. And last but not least, you should be able how to draw octahedral. Straight line, and then in the middle we have a square, like this. So the angle between the straight line with the middle one is 90 degree, and between the angle between the adjacent atom in the middle part also 90 degree. Before we moving forward in details discussing about the molecular geometry, here are a few terminology you should understand. First is the electron domain. Electron domain is the region about the central atom, or the region around the central atom, in which the electrons are likely to be found. Second terminology is the bonding pair of electrons. It's a pair of electrons that are shared by the atoms. Last is the non-bonding pair of electrons, or another name is lone pair. A pair of electrons assigned completely to one atom. So this schematic diagram is show the the uh, the shape of the electron domain for the bonding pair, and also the electron domain of the lone pair. If we have a bonding pair between two atoms, the electrons are attracted to each other. So it's meant that the electron domain distribute symmetrically ataupun distribute equally. But if we have lone pair, only electron belong to one atom, the electron domain separate evenly, or separate unsymmetry, because there is no attraction between two atoms. So this is the most important point also. If we have any Lewis structure that we draw from the chemical formula, we should be able to calculate how many bonding pair, how many lone pair. So for this ammonia, we confirm this is the Lewis structure. It consists of 4 electron domains. The 4 electron domains is composed of 3 bonding pair of electrons. 1, 2, and 3. And 1 lone pair. It has 1 lone pair here. So this is another example of compound. For this example, we identify they have three electron domains, two bonding pair, first and second, and one lone pair here. So remember, each multiple bond, either double or triple in any molecule, also constitute single electron domain. This is why even though it is a double covalent bond, we consider it one bonding pair. In general, the electron domain consists of lone pair, single bond, and multiple bond. So we have to more focus because start from this slide, we're gonna to learn how to predict the geometry of any compound. We use the VSEPR theory in order to predict the geometry of molecules or ions. So what is VSEPR? V is a valence, S shell, E electron, P pair, R repulsion. VSEPR. Valence, shell, electron, pair, repulsion. So the molecular geometry is predicted from its electron domain geometry. This is the reason from the Lewis structure, you should know how to count the number of electron domain. The electron domain is the combination between the bonding pair of electron plus lone pair of electron. In order to predict the molecular geometry, you should know the total number of electron domains, as I mentioned before. The electron domain is a bonding pair plus lone pair around the central atom. So, if we have electron pair or electron domain of 2, the electron domain geometry is linear. If we have electron domain of 3, the electron domain geometry is trigonal planar. If we have electron domains of 4, the electron domain geometry is tetrahedral. If we have electron domain of 5, the electron domain geometry is trigonal bipyramidal. If we have the electron domain of 6, the electron domain geometry is octahedral. So, again, remember the name, and also you should know how to draw the geometry for this each name: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and also octahedral. Here is the step how to predict the shape or the geometry of the molecules using VSEPR model or VSEPR theory. First of foremost, of course, you should know the molecular formula. From the molecular formula, you can draw the Lewis structure because we need the Lewis structure to know what is the electron domains. From the Lewis structure, we can calculate how many bonding pairs, how many lone pairs. It can tell us the electron domains. From the electron domain, we can know the electron domain geometry. Electron domain of 2 tetrahedral, electron domain of 3 trigonal planar, electron domain of 4 uh, electron domain of 3 is trigonal planar. Electron domain of 4 is tetrahedral. Electron domain of 5 is trigonal bipyramidal. Electron domain of 6 is octahedral. From the electron domain geometry, and then last we can decide what is the molecular geometry. So in this point, you should remember electron domain geometry is not similar with the molecular geometry. So we try to observe this particular example. We know ammonia, the molecular formula is NH3. From the molecular formula, you already know how to draw the Lewis structure. This is the Lewis structure of the ammonia. So, from the Lewis structure, we can tell what is the electron domain because we can count the bonding pair. For the ammonia, they have 3 bonding pair, 1, 2, 3, plus 1 lone pair. So for the ammonia, the electron domain is 3 plus 1 equal 4. If the electron domain is 4, so the electron domain geometry is tetrahedral. However, due to the presence of due to the presence of lone pair in the ammonia, the geometry is no longer tetrahedral. So the geometry changed to trigonal pyramidal. Okay. So this is the tetrahedral like the chicken feet because of one lone pair. So it's not longer tetrahedral, but it just like a pyramid. So we name it is the trigonal pyramidal. It's like the pyramid. Okay. Okay. Due to the one lone pair. So the presence of lone pair in any molecule will change the electron domain geometry. In this case, the tetrahedral become trigonal pyramidal. If let's say the compound have another lone pair, let's say 2 lone pair, like the one that we found for water. So the geometry also different. It's no longer trigonal pyramidal, but for the water, it become band. It become band. Or another one, another name, sometimes we call it V shape. Band or V shape. This is band. or V shape. So the numbers of lone pair will determine the molecular geometry. For this tetrahedral, one lone pair is trigonal pyramidal, two lone pairs is band. So we're gonna to recognize the molecular geometry respective the number of lone pair. If we have electron domain of 2, the 2 plus 0, no lone pair, so the geometry is the electron domain geometry is linear, so the molecular geometry also linear. If we have electron domain of 3, we know electron domain of 3 is the trigonal planar. If no lone pair, we call it trigonal planar, like this, trigonal planar. But if we have the electron domain of 3, electron domain of 3 with one lone pair, 2 plus 1 is not longer trigonal planar, it become band because of the presence of one lone pair. It become band. First, trigonal planar, and then one lone pair, and then it become band. If we have electron domain of 4 with no lone pair, the molecular geometry is a tetrahedral. It looks like this, tetrahedral. However, if the electron domain of 4 consists one lone pair, so the first lone pair it should be here. So it looks like the pyramid. So the name is trigonal pyramidal, like this. If we have the electron domain of 4 with two lone pair, 2 plus 2, so another lone pair in here. So the molecular geometry is a band, like this. Okay, so the number of lone pair, 1 or 2, will change the final molecular geometry. Moving forward, if we have an electron domain of 5 with 0 lone pair, we know it is trigonal pyramidal, like this. Straight line, and then we have in the middle, and then 1, like this. So it's trigonal pyramidal. But if we have one lone pair, so the first lone pair it should be here. Okay, like this. Sorry, it can be here or can be there. In this case, we get the first lone pair. So the molecular geometry we call it seesaw. Seesaw. It looks like a seesaw. Jongkang jongket. Okay, straight and then like this. Okay. If we have electron domain of 2, so another lone pair is here. Sorry about this one. So another lone pair, two lone pair, one lone pair, second lone pair. So the molecular geometry is a T shape. It looks like a T. It looks like a T. But if we have three lone pair, so is the third lone pair like this. This is the third one. This is the second one. The first one of lone pair. The geometry become linear. Again and again, the number of lone pair will affect the molecular geometry. From trigonal bipyramidal, change to seesaw, change to T-shape, and last change to linear. Okay, the last one, the electron domain of 6, we know is a octahedral. How to draw the octahedral? Straight line, and then we have a square in the middle, like this. Okay. If we have no lone pair, so it's remain octahedral like this. But if we have one lone pair, the first lone pair is on the top, or it can be on the bottom as well. So the name is a square pyramidal. It look like a square pyramidal. Square pyramidal maksudnya, so this is a octahedral. If we do the first lone pair in the bottom one, we can observe this is a square, and then it's look like pyramid. This is why we name it square pyramidal. If we have two lone pair, so the second lone pair, it can be the bottom one or on the top one, is leave behind the square part. This is why we name it square planar. It just remain square like this. Because the top one lone pair, the bottom one is another lone pair. So we done about the molecular geometry. Remember from the electron, from the molecular formula, you have to draw the Lewis structure, and then you have to count the electron domain, bonding pair plus lone pair, and then you have to decide what is the electron domain geometry. They have 5 basics of electron domain geometry: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And then after that, very careful with the presence of the lone pair, because the presence of the lone pair will decide the molecular geometry. Okay, all right. So this slide is the additional knowledge. We're gonna to focus a little bit on the effects of the lone pair, and also the multiple bonds on the bond angle. For example, this is three different compounds. We have methanes, we have ammonia, and we have water. All these three molecules have tetrahedral electron domain geometry. Why tetrahedral? Because of electron domain of 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. However, the angles differ slightly due to the presence of lone pair. One lone pair and also two lone pair. As you can see, if there is a no lone pair for the tetrahedral, the angles ideally is 109.5 degree. But if we have one lone pair, it's changed from the trigonal, it's changed from tetrahedral to trigonal pyramidal because of one lone pair. This lone pair will reduce the angle. So from 109, it becomes about 107. So for the water, if we have two more lone pair, because the water is not longer tetrahedral, is a B shape or a band, is a band geometry or a B shape. The angles is reduced further from 107 to 105, 104.5 degree. The angles will be decreased is the number of lone pair increase. Okay, why the increasing the number of lone pair will reducing the value of the angle? This is the explanation. A bonding pair of electron is attracted by the both nuclei of the bonded atoms. The electron from this atom attracted to the nucleus of this atom, negative, positive, and then the electron from this atom, negatively charged, will be attracted into the positive charge of nucleus for the atom. So the electron are attracted each other. So the electron domain for this bonding pair of electron are distributed equally. If we have a lone pair of electrons, no bonding, the lone pair of electron is attracted primarily by only one nucleus. This is why the electron domain of the bonding lone pair is look like in symmetry. Because the lone pair experience less nuclear attraction. The lone pair no nuclear attraction. Its electron domain is spread out more in space than the bonding pair. So the electron domain is bigger than the electron domain in the bonding pair. Because of this electron domain of lone pair bigger in space, it exerts greater repulsive force towards the ejection electron domain. Thus, it reduces the angle. Okay. So because of the tetrahedral like this. Because of the lone pair, the electron domains is bigger in space. It reduced the angle. It reduced the angle. The angle is not longer 109. It become 107. It reduced further. If we have another lone pair, it can be reduced more, 104. Okay, due to the electron domain of the lone pair are spread more in space, so it produces a greater repulsive force towards the electron domain of the adjacent atom. Okay, so now is the effect of multiple bonding, double or triple, towards the bond angle. Because the multiple bond is containing of higher electronic charge density. What you mean electronic charge density? Single is 2 electron. Double is 4 electron. Triple is 6 electron. This is why multiple bond is contain higher electronic charge density than the single bonding. So this is the example to show the effect of the multiple bonds towards the bond angle. So in this case, the electron domain is the electron domains of 3, 1 to 3. So the molecular electron domain geometry, it should be trigonal planar. In ideal case, it should be 120. Okay, 120, 120, 120, and also 120. However, because of the presence of the multiple bond, in this case is double bonds, so the electron density is greater. So because of this double bonding, the electron density will push or will reduce the angle. The angle will be reduced to a small number. In this case, it reduced from 120 to 116. However, the angle here, the angle here, it increased from 120 because of the presence of multiple bonding. It become bigger, 122. From 120, it become 122. Don't need to worry about the numbers as long as you can understand the effects of the lone pair and also the effect of multiple bonds towards the angle is good enough. Okay, so this is the explanation. Because the central carbon atom is surrounded by 3 electron domains, 3 bonding pair plus no lone pair, it expected trigonal planar geometry with 120-degree bond angle is shown in the previous slide. The reasons of double bonds seems to act much like a lone pair of electrons. The double bond will reduce the bond angle from the ideal number 120 into actual angle 116 degree and 122 degree. I already explained this statement in the previous slide. So the electron domains for the multiple bonding will produce a greater repulsive force. It's similar to the lone pair on the adjacent electron domain than the single bond. So I think this is going to be the last slide. From the previous slide, we try to predict the geometry of a simple compound. So it's meant that one compound is one geometry. However, we also can predict the geometry for the larger molecule. As long as we can identify the central atom, we can count what is the electron domain, what is the bonding pair, what is the lone pair around that central atom. We can tell what is the electron domain geometry, and we can tell what is the molecular geometry. Okay. So this is the example. Let's say we focus for this carbon. As we can see, this carbon has 4 electron domains. 1, 2, 3, 4. 4 bonding pairs with no lone pair. So the electron domain is 4. Because of this, the electron domain geometry is a tetrahedral. So the molecular geometry also tetrahedral. Why tetrahedral? Because there is no lone pair. If we go for this carbon, we count the electron domains is 3. 1, 2, 3. Double bond is considered 1. 1, 2, 3. So the electron domain of 3, the electron domain geometry is trigonal planar. Because of no lone pair, the electron domain geometry with the molecular geometry are similar. So the molecular geometry also trigonal planar. But a different case for this oxygen atom. We know the electron domain for this oxygen atom also 4. 1, 2, 3, 4. However, they have 2 lone pair. Because of the electron domains of 4, the electron domain geometry is a tetrahedral. Due to the presence of 2 lone pair, 2 plus 2, the geometry is no longer tetrahedral, it becomes band. Tetrahedral, 2 lone pair, first lone pair, second lone pair. So the geometry becomes band. Okay, so I hope you can understand how to predict the geometry for the larger molecule. Identify the central atom, counts what is the electron domain, determine what is the electron domain geometry, and then if it has a lone pair, the molecular geometry will be differ slightly, it depending on the number of lone pair. So this is the geometry is look like tetrahedral, trigonal planar, and also B shape of band. So they have two lone pairs. Okay. So you can try by using the SEPR model to predict the molecular geometry of this example. The answers is already given in the right hand side. So yeah, you should try, and then you can check your answer with the provided answer. I think by so we already finished for this molecular geometry. I hope this recorded video will help you a lot in order to understand the molecular geometry. It's very simple using the VSEPR theory. First, molecular formula, Lewis structure, count the electron domain, predict the electron domain geometry, and then decide the molecular geometry upon the number of lone pair. I think it's quite easy. Then last, thank you very much for your time to view this recorded video. And see you again in on our next class. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh, and bye bye.